Hello, and welcome to the Central Force Warriors NECAP Chemistry Review. The question for today is, what's the matter? Yep, you guessed it right. Chemistry is the study of matter and how it changes. So today we'll be looking at matter, which is anything that takes up space and has a mass. And matter is everything around you, and it's made up of atoms and molecules. All right, let's get going then. First things first. Matter can come in 5 different versions or to 5 different states, and as you can imagine, we have the standard solid, liquid. So we have solid, we have liquid, we have gas. But as you get hotter and hotter this way, you're going to end up with plasma. It's really hot, really unbelievably energetic a state. And then if you go the other way and you get to something really, really cold, you get a very unique state called the Bose-Einstein condensate. As you can imagine, this has to do with energy and the way that energy flows. So solids require energy this way to become liquids. Liquids require energy to become gases, and gases will require energy to become the plasmas. Here on the bottom left of your screen, you will notice that you will take energy to go from solid to liquid, from liquid to gas, and then you will release energy going the other way around. And so remember also that the states of matter relate directly to the space in between the molecules and their movement. So solids here have very tight molecules that are basically not moving past each other, but what they're doing is they're just vibrating. When you get to liquid, by the time you get to liquid, you have some movement, and eventually with gas, you have the most movement, the most space between the molecules, the most energy. Okay. Let's go on. So there's 2 ways that you can change matter. The easiest one is to think of it as a physical change. A physical change requires you to take a compound or an element and convert it from one state to another. You go from solid to liquid. In this case, we have from liquid water into solid, and you can also revert this back. The other way around, however, is to have a chemical change. And a chemical change would actually ask you to break the intramolecular bonds. So you're actually taking water and you're separating it so that the oxygen becomes one thing and the hydrogen frees up. That is a chemical change, and it's usually non-reversible. So this is non-reversible as opposed to this, which is reversible. Okay? As you know, atoms are made up of subatomic particles. We used to think that atoms were indivisible. We know now that's not the case. So we can divide them into 3 basic parts: protons, neutrons, and electrons. And they go together something like this. Inside of the nucleus of the atom, we have protons and neutrons. And then outside, spinning around like crazy, we have these things called electrons. The neutron, which is the first of the molecules I'm going to speak about, is very large. It has a mass that is accounted for, but it has no charge, so it's neutral, as the name implies. Then we go over to protons. The protons are positive, remember that, and these positive charges are going to be fighting each other in the middle, because remember, these guys are all living together here. So the job of the neutron here is basically to relax these guys, to hold them together so that they can live in peace, even though they have conflicting charges, because they have opposites attract and same charges repel. So they're repelling. The neutron's job is to actually hold them together. The last one is going to be the electron. The electron is the smallest of all of the subatomic particles, and it actually does have a negative charge. So here's your negative charge, but it has such a small mass that we don't even count. It when we're considering the weight of an atom. So what happens if you change things? So let's look, for example, at the carbon atom, standard carbon atom here. We know that the atomic number is 6, which is also the number of protons. And what that tells us is basically this: we have 6 protons, and then by default it means we also have 6 electrons, because it is going to be in neutral, normally standing in neutral. If I change the number of protons, if I take the proton and I get rid of 1 and make it 5, I no longer have carbon. Or if I add a proton, I also don't have carbon anymore. I'm now going to nitrogen. So the number of protons has to be the same if I want to keep the same atom. Now, if I want to change the number of electrons here, for example, we have 6 electrons, and I get rid of one of the electrons, that means I have left behind a positive. Because if I get rid of something negative, I have left it more positive. In this case, if I get rid of an electron, I still have carbon, but now I have a positively charged carbon. In other words, one without an extra electron, without an electron. I can also add an electron and I can make it into a negative carbon. Lastly, if I take a neutron, so now we take a neutron as a positive and I get rid of a neutron, I still have carbon because carbon is still 6 protons. But what I have done is I have changed the mass. So I have made it a lighter version of carbon or a heavier version of carbon. And that becomes important when we think about radioactivity, which we're going to do next. How do we read the periodic table? It's very simple. Each of the elements of the periodic table, there's 92 naturally occurring elements, and there's a couple of dozen man-made elements, which are the later part of the periodic table. When you look at the periodic table, the first thing you have to worry about is the number. That's the atomic number. As I mentioned just a bit ago, that tells us the number of protons and therefore the number of neutrons, the number of electrons in a neutral atom. The C is going to be our symbol, which allows us to look very quickly at the element we're looking for, and then sometimes you're going to have the name. Last and most important is the atomic mass. This mass is made up of the addition of the protons and the neutrons. So we also know that not all of the carbons are created equal. Sometimes there's some carbons that are a little heavier, and sometimes there are carbons that are a little lighter. In other words, some of the carbons are either missing some of the neutrons that are normally found there, or they have additional neutrons. And so we know that this atomic mass, in this case 12.01, is actually the average number. That's the one that's listed. Now let's look at the periodic table and why it's such an awesome tool. You may remember, let's start by thinking about these guys. You may remember these guys. These guys are the noble gases. They're the royal family of the periodic table. They have complete valence shells and everyone wants to be just like them. They don't really react. On the other hand, we do have some elements that are hanging around with some extra electrons they'd like to get rid of, or that they need electrons in order to be completely filled. Periods go this way, and there are some commonalities between these rows as you see across, and what they will do is you will see the increasing number of electrons being filled until you get to the ultimate noble gases. But more importantly for us is going to be the groups. So I want you to look at the groups really quickly, and let me just change the color real quick. Okay, when you look at this group right here, these guys that are here in red, that I just circled blue, those guys are very much in need of losing that electron. They have one electron over here. They have one electron that they really like to get rid of. Because if they get rid of the electron, they will be just like these guys. So number 3 right here, lithium, will be just like helium. Number 11, sodium, will be just like neon. And these guys, on the other hand, are dying to gain an electron so they can also feel just like these guys. So everybody wants to be like this. These guys they need electrons, and these guys have extra electrons. And these trends will continue on with each of these groups until you get to about here. These guys, for example, number 4, not much reactive because it's really difficult to put on 4 electrons or to lose 4 electrons. Instead, you're going to make a special kind of bond called a covalent one. So let's look at one of the questions from the released items from NECAP. This question says element X reacts with potassium to produce a compound which is K2X. The table below shows several different elements. Which one is the correct one? I'll give you a minute to look at it, or a second just to look at it. First thing you got to do is you got to find potassium here. We find it. We know it's in this first column, which means that it's the group that has 1 extra electron to give up. So if it's going to be with a 2, if it's K2X, we're looking for an element that needs, or that'll be happy with 2 electrons. So if we look, it's not going to be these guys. Obviously none of these guys. That would be completely wrong, because these guys don't want to share with or have anything to do with anybody else. It would have to be someone on this column, because this column is the one that's missing 2 to be completely full and happy like these guys. In this case, we look down and we look at hydrogen. Nope, it's in the first column. We look at nitrogen. Nope, it's in this column. We look at oxygen. Ding, 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 ding. Here's our winner. Oxygen would be our winner because it would be happy with 2 of these potassium electrons hanging around it. Okay, let's look at another question. This one says, which chemical property places neon and argon in the same group? Well, if you went back for a second, you would see that neon and argon, and neon and argon being right here, are going to be happiest when they already have a complete full outer energy shell, so the answer here is B. It's not ionic compounds. They would not form ionic compounds. And this is irrelevant, this is also relevant, so the answer would be both, because they're both in that group, which is the noble gases. All right, chemical reactions, really, very quickly. I don't want to make this too long, but we know that there are two important chemical reactions. One is called the ionic bond, and just like in human reactions, if what you have is the giving up of electrons and the taking of electrons, just like in human relationships, it's not a very strong bond. Ionic bonds require sodium, which is in the first column, to give up this electron to come back and make chlorine happy. And so they are basically giving up an electron, getting an electron. It's a good bond, but it's not a strong bond. The stronger bonds are the ones where you're actually sharing, because you're both winning from this. And this is called a covalent bond. And in this case, this hydrogen that would really like to feel like it's got two, what it will do is it will take these two electrons right here and it will share. So at this point, hydrogen feels like it's got two, this hydrogen feels like it's got two, and then this oxygen right here feels like it's got 8. It feels happy, it becomes 10. So this hydrogen feels like helium, and this oxygen feels like neon. All right. The other thing I've seen before is this idea of chemical reactions, exothermic and endothermic. And what you have to consider for these is the idea that there is energy required and energy left out. You start with the reactants and you end up with the products here, right? In an exothermic, which is exit, energy leaves, you start with more energy and then you lose energy by the time you finish. In an endothermic, bringing it in, you have less energy and then you end up with more energy at the end. One thing is the idea of a catalyst, which speeds up chemical reactions by lowering this activation energy for a reaction to take place. Review that one. Here's a question from NECAP. Let's see how we do. Which statement best describes the kind of reaction that takes place on this graph? First answer is the reaction is exothermic. The products have less energy than the reactants. Well, we notice that the reactants have less energy than the products. The products have more energy at the end. So if they have more energy, it has to be the energy going in, so it's going to be endo. So we know that much is endo. The reaction is endothermic. This one may be a winner here. Let's see. Endothermic because the reactants have more energy than the products. No, that does not work. The reaction is endo because the products have more energy than the reactants. Here's your winner right here, ladies and gentlemen. It is C. Make sure you understand how I got that. Okay. Here's another sample. This idea is of radioactivity and the idea of half-lives. So when you look at half-life, this one says a rock sample containing any grams of potassium-4019, isotope with a half-life of 1.25 billion years. How much potassium-40 isotope will remain after 2.5 billion years? So you go from 80, and you would have to take half of 80 would be 40, half of 40 would be 20, and so the answer here would be 20. I can review this with you separately. I don't want to spend too much time, but this is another good example of the kind of questions that is asked in the NECAP. Lastly, I want you to remember, review the type of chemical reaction, single replacement, combustion reaction, double replacement, all of those. If you have any questions, you can always watch the crash course for chemistry in YouTube. Just simply type in crash course chemistry and you get Hank Green. I cannot emphasize enough, ask your teachers for help if you have any questions at all. And lastly, use the reference sheet. The sheet that you will actually have during the exam is available to you now. Get it from your teacher, look at it, memorize the periodic table as much as you can in order to not waste time during the exam. I want to leave you with this thought, as always. You can do it. And my buddy over here, Walt Disney, writes, if you can dream it, you can do it. I dream that you can do it. This is going to be the best year for NECAP for us. So let's get this together. Let's make it happen. I hope that was helpful.